Welcome to this course on computer software and applications. In this series, we will learn how computer software tools are used for solving mathematical problems, simulating electrical systems, analyzing devices, and processing data. The course is structured into two modules. Module 1, Computational Methods and Mathematical Modeling. Module 2, Simulation, Design, and Statistical Applications. Let's begin with Module 1. Module 1, Computational Methods and Mathematical Modeling. Lecture 1, Review of Matrix Operations and Numerical Iteration Procedures. The foundation of computational analysis begins with matrix operations. Matrices provide a compact way to represent systems of equations, which appear frequently in electrical and physical systems. 1. Matrix operations. Common operations include addition, subtraction, multiplication, inversion, and decomposition. For example, multiplying matrices allows us to model state transitions in dynamic systems, while matrix inversion is essential for solving simultaneous equations. 2. Numerical iteration procedures. Iteration is the process of repeating calculations until a desired level of accuracy is achieved. Methods such as successive substitution or Newton's method are widely used in computational problem solving. These methods are particularly important when analytical solutions are too complex or impossible to obtain. Software tools like MATLAB or Python-based platforms can handle these operations quickly and accurately, making them essential for engineers and scientists. Lecture 2, Solution of Integral Differential Equations Using Programming Software. Electrical and physical systems are often governed by integral differential equations, which combine differentiation and integration. 1. Why integral differential equations matter? For instance, the current in an inductive circuit or the voltage across a capacitor can be described using such equations. 2. Solving with software. Programming platforms like MATLAB, Simulink, or Python libraries provide built-in functions for solving differential and integral differential equations numerically. The user defines the system equations. The software applies numerical algorithms, such as Runge-Kutta methods, to approximate the solution over time. This approach allows engineers to model and simulate real-world behaviors without resorting to manual calculation. Lecture 3, Mathematical Modeling of Electrical Systems and Devices. 1. What is mathematical modeling? Mathematical modeling is the process of expressing the behavior of a system using equations. For electrical devices, these models describe relationships between voltage, current, power, and other parameters. 2. Types of models. Physical models describe fundamental laws, such as Ohm's law and Faraday's law. State space models represent systems in terms of inputs, outputs, and state variables. Equivalent circuit models simplify complex devices into resistors, capacitors, and inductors. 3. Applications. Modeling is the first step towards simulation and design. Once equations are set, software tools can be used to analyze system performance, predict responses to different inputs, and optimize design choices. Lecture 4, Dynamic and Transient Simulation of Physical Systems. Systems rarely operate in steady-state conditions all the time. Dynamic and transient simulations are essential to study behavior during changes. 1. Dynamic simulation. Dynamic simulation examines how a system evolves over time. For example, how motor speed responds to varying loads. 2. Transient simulation. Transient simulation focuses on short-term changes, such as voltage surges when a switch is closed. 3. Software applications. Simulation software like Simplr, MATLAB, or ANSYS provides the ability to run both dynamic and transient analysis. By inputting system equations or models, the software generates time-based plots of current, voltage, speed, or temperature, showing how the system reacts under real operating conditions.